So I'm going to show you an example of building a bot to do Q&A on the FSDL Discord based on the information that's contained in previous FSDL classes. And so this bot is running live in the Discord now. So if you go to Discord and then you go to the Ask FSDL bot channel, you can play around with this as we talk and like try asking it questions and see what works and what doesn't work using this /ask command. I also posted in the LLBC SBTB 2023 general channel, the channel for this class, a link to the GitHub repo where you can follow along the code that we're going to talk through. And this is also like, if you don't have this link, you can just go to GitHub/thefullstack, and it's the Ask FSDL repo there. So, what are we going to talk about here? So the basic architecture of this system is kind of like a simple implementation of the reference architecture that we've been talking about for most of the day. So we're going to start with different sources of data. And these sources of data come from like different data that we have from previous classes. So it includes the text on the website, on the FSDL website. It includes the YouTube videos, like the recordings of the lectures and the transcriptions of those recordings. So like all the different sources of information that we have about like what's happened in previous classes. And so the first thing that we're going to need to do is we're going to need to take all of that information, like raw information, and we're going to need to store it somewhere in a format where we'll be able to do stuff with it later. And so we'll run an ETL process on that raw data to put it in data storage. Then once we have the raw data, we're going to need to embed each of those data points, store in a vector index. We will have that vector index interacts with a serverless backend. That serverless backend, what it does is it takes the questions that you'll be asking in Discord, which are processed by a Discord bot server, and it combines those with data from the vector index and a prompt for the base LLM to produce a response. That response goes back to the Discord bot server, which then forwards it along, like formats it for Discord and forwards it along to the Discord channel so that you can see the answer. And the tools that we're using for each of these steps, again, these are just examples of the many different types of tools that you could use here. But we'll be using a tool called Modal for the ETL. Modal is like a serverless backend tool that makes it really easy to turn Python functions into serverless functions that you can run on other infrastructure. So it's helpful for many things, among which is like parallelizing kind of computation expensive tasks like ETL. Then we'll be storing the data in MongoDB and their hosted option MongoDB Atlas. We will be embedding that data, storing it in Pinecone. Our serverless backend will be, again, hosted in Modal. Our Discord bot server will be hosted on AWS. And then the LLM that we're going to use is going to be powered by OpenAI. So again, just one's individual choices of many. And again, you can try this out on your own. Ask FSDL bot channel in the Discord. So play around with this. And then if you want to follow along in the code, it's github.com/thefullstack. And so this is also, didn't want to do like a live coding thing today because I think it's just tough with a group this size, but you should be able to run this on your own if you want to like try this out and make changes to it and explore the code base a little bit more. So with that, let's take a look at what's going on here. So I will start with the data. So I mentioned the data was like a representation of each of the different kind of sources of information that we have that kind of make up the body of knowledge that is that is FSDL. And so the way that we've stored this information is we've stored it as like kind of manifest files that keep track of all the individual types of documents and information, but are not the raw data themselves. Instead, they're just pointers to that data. So showed this example before, but we have the URL for where the raw lecture notes are stored alongside the individual lecture examples. So these are the different lectures that are stored as like part of the FSDL corpus. But then we also have other sources of data here in the kind of full bot that we didn't talk about this morning. So we have references to LLM papers that include the title of the paper, the archive link, as well as different tags that are relevant for like what type of queries they're gonna be used for. And then we have the IDs of the videos themselves. And so this is like, you can think of this as like a manifest file. And the reason why we do it this way is that like typically not really best practice to store large amounts of raw data in GitHub. It's, if you want to version control things, it's helpful to use GitHub to just store like pointers to the data, but then store the data itself elsewhere. So that's the data piece. The next part of if we go back to our diagram here, the next part of the pipeline after the data itself was the ETL process. So how do we take that raw data, download it, transform it, and store it in our data storage? And so let's look at the ETL code itself. And maybe we'll focus on the specific example for Markdown. So this is a good point to kind of like tell you a little bit about Modal, which is the tool that we're using for ETL. So again, Modal is like a really easy way to manage serverless compute in Python. And the way it works is it kind of treats like the infrastructure that you're running things on as like basically just like Python objects. So in this case, we have a Modal image. Oops. So we look at the shared code here. We're defining a modal image. And this modal image is an image that uses a container that's based on Debian Slim Ubuntu distribution with this particular version of Python with the following packages installed: LangChain and MongoDB. And so what this does is it defines for Modal, hey, whenever I use this image to run a function, this is the Docker container that's going to be running behind the scenes to actually provide the resources to run this. And so let's see. So if we go back to our ETL process for Markdown, we start with this base image that we defined that had those two dependencies, those two Python dependencies. We install some additional Python requirements, and then we define a stub, which is, a stub is like a combination of the raw image alongside of like anything else that we want to provide to that computer when we run it. So in this case, we give it a name, we specify some secrets, like some API keys that we want to pass in, as well as some mounts, so like some local files that we want to attach to it. And then stubs in Modal are things that you can just run. And so whenever you run a stub, it basically takes care of translating how to actually run that code on the physical infrastructure in a way that where you just don't have to think about it. It's just like running a Python function, but Modal knows what are the requirements for that computer and the image that's running on that computer in order to run this function correctly. And so in this case, we have like a simple sort of like coordination script that we're going to define as something that we run locally on this machine. And what this does is it loads like all of the JSON that we have that defines the corpus of Markdown files that we want to read. It has the logic for how you combine these URLs. Like if you remember, we had a base URL and then a stub. So how do we combine these things into the ultimate URL that we want to download? And then we take each of these documents and we map this toDocuments function on them. So this toDocuments function, what this is doing is it's downloading the text from the URL. It's splitting up the headings, and then it's basically taking these documents and adding some additional metadata to them. And so the key thing to understand here is, like, basically, without understanding necessarily all the details about how this ETL works, what this is doing is it's parallelizing the process of taking each of these files that we have stored somewhere else and preparing them to store in our document store. So it's splitting them up, it's handling the metadata, and it's putting it all back together in a way that we can put it in the document store. And each of these kind of ETL scripts works pretty similarly. So we have one for Markdown, we have a different one for PDFs, which processes the PDFs differently, and we have a different one still for videos, which takes these videos and gets a transcript for them and extracts like kind of the text from those transcripts to use for ultimately for embedding. So any questions on like kind of the data or ETL piece of this? I guess I sort of glossed through some of the details here, but I feel like this is maybe one of the less like LLM specific pieces to understand here. Cool. So next thing, let's talk about the vector index. So let's see, let me.
Sorry.
Yeah.
I have a question. So for this test, for the MongoDB, we have to set up somewhere in the cloud for the Mongo Atlas?
Can you say that again?
No, for the ETL process, it needs to store in a data store. Is it MongoDB Atlas?
Yeah.
That we have to configure still, is it? Or
Yeah,
is
so you still need to configure MongoDB separately. And so I think we have that documented somewhere here. Yeah, maybe under setup. So there's a set of instructions here that walk you through, if you want to run this on your own, connecting how you actually set up MongoDB and connect it to this FSDL repo.
Got it. Okay, thanks.
And yeah, so it's worth noting that like under this setup folder, there's a set of instructions here if you want to run this on your own, how you set this up from scratch. And so this involves kind of updating an environment file, preparing your Python environment, setting up your managed services like Modal, OpenAI, and MongoDB. And then, and like once you have those things set up, then you can actually run the ETL, which downloads all the data, processes it, transforms it, loads it into the document store, creates the vector index, runs the back end so that you can interact with it. So this is, if you want to follow along or do this on your own, this is the right starting point, the set of instructions to follow. Okay, so let's look at what's going on here when we make these documents storable, like indexable in the vector index. So if we look at the make file, what we're looking for is the make vector index command. And so what this is doing is it's running this this file from the app, or this command from the app using Modal. So Modal run just says, hey, I want to run this using Modal, which allows me to run this on the cloud in Modal's infrastructure using the environment that I specified. And we're going to run this create vector index command from this file. And we're going to point it to the specific Mongo database that we set up and the specific collection within that Mongo database where we want to store this stuff. Because these are configuration level things that you'll set up when you're building this application for the first time that are specific to your instance of MongoDB. But the logic is contained in this app.py file. And so if we search here for create vector index, then we can see that this is a function, like a modal function. So this is something that we can call, and it'll run it on the image that we defined above. So again, it's a Debian container with some additional Python requirements installed, including face for vector storage and similarity search, MongoDB client, Gradio for simple web UIs, OpenAI requirements like that. So on that machine, when you run this command, what will happen is you will connect to this Mongo database. You will pull the collection. So again, this is defined in your environment. You'll download the documents from that collection. You will then prepare these documents for the vector store, and we'll go into a little bit more detail about what this command does. But basically, what you're doing is you're taking these documents, which might be large, you're splitting them into chunks, and you're keeping the metadata alongside each of the chunks. So you can store alongside the chunk all the relevant information about the document that contains it. Then you we basically create an index in our embedding vector store, and we index each of these chunks, and then we save this embedding index locally. So again, simple example. So we're following a simple pattern here of like creating and storing index locally, but in production you might be using a vector database, Pinecone or something like that to do this. Any questions on what's going on here? I believe, if I remember correctly, we're just using the local face for this. Yeah. But you could swap this out for Pinecone if you wanted to do this in more like a production-oriented way. Other questions? Mm-hmm. Can you say that again?
So face is both embedded model and the vector store, right?
So face is just the vector store. Face is just the vector index. And so when we run this function, so we're running this embedding engine, which is going to actually run these embeddings for us. And so we can look at what that does in a second.
Okay, got it.
Is that model is cloud agnostic? So when you run the kind of like a function into the image of the container, you can actually like tell model run this in GCP or AWS or somewhere else?
Mm-hmm. Yeah, so modal, like you can think of it as like, it's like AWS Lambda or something like that. It's like a serverless kind of function environment, but designed to be like really easily used from a Python environment. And so what's actually happening behind the scenes when you run a function like this is it is building a Docker container that contains all of the requirements that you specified, all of the secrets that you provided, things like that. It's running that Docker container on a remote machine somewhere. It's running the Python code in that Docker container on a remote machine somewhere, and then it's transmitting the results back to you, or back to the calling process, in a way where the calling process doesn't really need to know where the code was executed. Cool. Okay, so let's keep going here. Let's dig into this this vector thing here, right? So we're kind of glossed over some of the details here, where we ran a function called get embedding engine that is provided by this vector part of the code base, and then we use that embedding engine to create a vector index. So what's actually going on here? So let's look into this vector file. And if we look at the get embedding engine function, then we can see what's going on behind the scenes here is we are just creating a LangChain class that wraps in this case, the OpenAI embeddings for text embedding Ada 2. And this is just like a LangChain wrapper around the OpenAI embeddings that makes it easy to like call those embeddings on a chunk of a document. And so you can think of this embedding engine that's returned as just like a wrapper around the OpenAI embedding function. And so if we look at how this is used, we pass this embedding engine into this create vector index function. So we created a vector index using an index name, the embedding engine that we just got, as well as the chunks of text and metadata associated with those chunks of text. So what's actually going on there when we call this create vector index? So again, this create vector index is wrapping some LangChain functionality. And in particular, the LangChain functionality that we're wrapping is we're importing this wrapper that LangChain has around face. And then what we're doing is we are looking at all of the files that we're trying to embed. And we're creating the face embedding from these raw texts by passing in the underlying documents as well as the embedding engine. And so what's happening here is that the LangChain wrapper around face takes care of the work of running the embedding engine, which is just, again, a thin wrapper around the OpenAI embedding function on each of the chunks of documents, and then indexing those in face. So face is not running the embeddings, LangChain is running the embeddings. But LangChain has provided kind of this nice wrapper functionality around face that makes a consistent behavior between different vector stores for how to get documents into the vector store for a given embedding function. And so the nice thing about this is, so the not so nice thing about this is it obscures a little bit what's happening under the hood here, which is like we're actually calling the OpenAI embedding function on each of the documents, and then we're taking those chunks, those embeddings alongside the metadata, and we're indexing them in this face vector index. But the nice thing about it is it makes the behavior of how you do this relatively consistent between vector stores. So if we wanted to just, if we wanted to switch vector stores and use something like Pinecone, then we wouldn't have to change too much code. We could mostly just import a different vector store and change some like basic configuration about it. Any questions on how we're like taking the documents from the document store, embedding them, and storing them in the embedding index?
Can you talk a bit more like tokenization and, because there's the prepare function, because we need to chunk embeddings, chunks the documents and add metadata. So what's your intuition behind choosing the, how to tokenize like chunk size and like overlaps?
Yeah, so how to tune the chunk size. So unfortunately, it's pretty empirical. Like it doesn't always work the same way for every task. I can show you what we did here. So we, if you remember, we called this function called prep documents for vector storage. The way that this function works is it's importing, again, a wrapper from LangChain. And the wrapper from LangChain that we're using is the recursive text splitter. And so we create this recursive text splitter that uses a chunk size of 500 with an overlap of 100. And then we basically split the text for each document into chunks of around 500 with an overlap of around 100. Why chunks of 500 and overlap of 100? There's no real like theoretical reason for why you would do it that way. It's more just like you have to try a few different things and see which seems to work best for your use case. Trade-off being like, if you have smaller chunks, then there's more to search over. So the likelihood that you get the wrong thing back is higher. But then the chunk itself contains less information. And so if you get the right thing back, then it might be easier for the model to process or cheaper for the model to process at the end. But it might be losing also some surrounding information. Like if it's just, in the limit, if you just returned like 10 tokens or something, then you would just be looking for like keywords, and you wouldn't actually understand the meaning of the keywords in the context of the broader document. So I generally think like probably better to err on the side of using larger chunks with some overlap rather than trying to make your chunks too small.
And like how much do you invest into optimizing this, or just like try a little bit and move on kind of?
Yeah, I think like I would probably just pick something that seems reasonable to start, like chunk size somewhere between 500 and 1,000, and then what I would do is like I would follow like as you debug the system, when the system fails, you're going to want to look at why. So if you look at a failure and you look at kind of the execution trace and you see that like, actually, I don't think I could have figured this out because the model doesn't really have like this chunk of information that it got. Seems like it doesn't really contain enough for me to really answer the question. Then that might cause you to think like, well, let's see, maybe one hypothesis is that increasing the chunk size could help the model avoid this kind of failure. And so then you could try like increasing this chunk size parameter, rerunning your evaluation, and looking at the results again and saying like, okay, did the model get the answer right? If not, why not? Like, was I wrong? Was it actually not the fact that the model didn't have a big enough chunk of information? Or maybe like when you increase the chunk size, it caused some other problem.
Got it.
No, not necessarily. So it means that any like information that you need from this document should be contained in the chunk of size 500. But overlap between chunks can also create problems. Like you could have some information in the document where in order to understand the information, the model needs to look at two chunks next to each other. And so that's where the overlap comes in, because if like a sentence, or if a complete thought or a complete piece of information starts in one chunk, but then is finished in the other chunk, if there's no overlap between the chunks, then that's going to happen a lot. But if there's overlap between the chunks, then it's less likely to happen because you get you have the like that information is contained in both chunks. And so the more overlap you have, the less likely it is that you have like something that's important for the model to understand that is you can't understand because it's not fully contained in one chunk. But the trade-off is you're creating more embeddings because you're duplicating some of the information.
Right. And what happens if a fact, particular piece of information is longer than this overlap? It means that this fact is still split between two chunks between any overlap at all.
Yeah.
What will the outcome be?
Well, the outcome would be you might retrieve a document that would be relevant, but the model can't interpret it correctly because it doesn't have all the information it needs to interpret it. And that kind of failure happens all the time with these systems. Like the chunking is, I think, one of the most, one of the easiest things to get wrong about these systems and one of the hardest things to tune. And like if you think back to the OpenAI example, if you remember, there was like that chart where it showed like the increases in performance of trying different things. And at first they were like 45%. And then the first jump was like 45 to 85 or 45 to 65. And they tried three things, right? It was like, one was hypothetical document embeddings, another was something else. And then the third one was tuning the chunks. And the only thing that actually worked was tuning the chunks, and it had a huge increase in performance. So this is a place where you just, mostly need to be like pretty experimental to see what works for your document corpus.
Thanks.
So when you have the overlap, there is no restriction that you need to pass just one of the chunks, right? You could send like the top 3 or top 4, and even if the answer is not there towards the end of the other chunk, it should still be able to retrieve from the continuous path, right? There is no limitation on that.
Yeah, so the trade-off is like, with smaller chunks, it's more likely that you're gonna get an incomplete thought in one of the chunks, but then the chunk itself takes up less of the context. So if you have small chunks, then that means you can pull a lot of chunks and pass all of those chunks into the model's context. And so that means that, like, at the limit, like, let's say that you have one chunk. Let's say that your chunk size is so large that you can only fit one chunk into the context. Then that means that you have to, your retrieval system has to be really, really good, because it always has to get the right chunk. It always has to get the right chunk in the top, as the top one. On the other side, like, imagine that you have you can fit many chunks. You can fit 100 chunks. And then that means that the right answer just has to be in the top 100. So it's putting a lot less burden on the information retrieval system. But there's it's a lot more likelihood that a chunk will not really be able to fully answer the question. Cool. Okay, so let's see, where were we here? Let's go back to our make file. Actually, let's just ground this in looking at the setup again. So again, like, skipping through this is just your setup. But the first thing that we did is, well, after we extracted the document and put it in the document store, then we created our vector index. And so again, what was happening there is we had called the appropriate LangChain wrappers to pull all the documents from our document store, chunk them into chunk sizes of 500 with an overlap of 100, embed them using OpenAI embedding model, and store them alongside the metadata for the document in our vector store, which in this case is just a copy of face running locally. And we save that index to disk. So the next thing that we will do is we will actually run the backend. So let's look at what we're doing when we're actually creating this backend web service. So what we're doing when we run this backend service is we are calling this task called run backend modal. And what this task is doing is we are running a modal command, either serve or deploy on this file app.py. And so let's go back to this app.py file, which defines a lot of our application logic that's running in the backend for modal. And let's look at what this task is actually doing. Oh, apologies, I think sorry, this is actually just a modal thing. So we're either serving this as a local thing where changes to the local file will trigger an update, or deploying it, so it's something that other folks can use. But either way, it's running this this full app. And so the kind of front end to this is the web service itself. And so we're telling modal, I want to run this as a container, again, that is running this particular image. And it's connected to this particular network file system. But one of the cool things about modal is that you can also take this running container and expose it as expose a web endpoint on this container so that services outside of modal can interact with it. And modal makes it really easy. Like, you just define this additional wrapper here, which is you define a web endpoint with a get method. And so what this service is doing is it's taking our Q&A chain and is exposing it to queries via this web endpoint. So it's like taking a query, which is the request that we're going to send to this server. It's passing this query into this function called Q&A, and then it's returning that answer. So what is this Q&A function doing? So this Q&A function is, well, like one like fun detail to know about this Q&A function is, again, if you look at the modal definition we have here, like one of the pain points about using serverless functions is that like when they, if you're constantly calling the serverless function, latency is really low because the container is constantly running. But if you are not constantly calling that serverless function in a Lambda or something like that, then what happens is it'll spin down. And that's an intentional benefit of serverless functions. It saves you money because if people aren't using it, you're not paying for it. That's like one of the core benefits of serverless. But it creates problems sometimes because then when you call it again, the system has to spin up the container again, and that takes time because it has to load all the information from disk, it has to find an available machine. And so you can, in modal, you can specify a parameter called keep warm, which says, hey, don't get rid of this container, even if no one has called it for at least 1 second. And that means that you're gonna have, like if you have requests that aren't happening very frequently, you'll have a lot lower latency for those requests as long as it hasn't been more than a second. Let's come back to this Q&A function and let's talk about what this is doing. So again, we're taking this query that the user passed, the question that you want to ask about FSDL, and we are running this through our LangChain. And so we're loading from LangChain a loader function to load this default question answering chain. And we're gonna call this model, we're gonna call this chain with a particular model as the backend. And in particular, it's gonna be this chat OpenAI model, which we'll talk a little bit more about in a second. So what's going on here is we are recreating our embedding engine. And again, if you remember, this is just a wrapper around the OpenAI embedding function. And the reason that we're creating this again, that we're sort of reinstantiating this wrapper around the OpenAI embedding function, is because we want to be able to embed the query and then use that to find similar documents from our corpus. So what we're doing here is we're doing exactly that. We are finding the sources that are the closest to the query in the vector index, and we're returning those along with their closeness scores. And the way we're doing this is that like the vector index, this like kind of LangChain wrapper around the vector index, provides just an easy to use function called similarity search with score, which takes the raw query, embeds it using the vector embedding engine, and then finds the 3 nearest neighbors. So, and what we get as a result is like the sources, the chunks that we're gonna use, as well as the scores, the similarity scores. So then the next part of the chain is, what do we actually do with those similarity scores? Or with those chunks and those similarity scores? So next thing we'll do is we'll instantiate this, this LangChain wrapper that wraps GPT-4 with certain hyperparameters, which in this case we're using a temperature of 0 and a max tokens of 256. And then we are instantiating this question answering with sources chain, which is gonna wrap a lot of the functionality of taking the question, the chunked documents, and wrapping them in a prompt in order to answer the question. And then we are running this chain that we just loaded, on our input documents, like our source documents, as well as the question. We take the result, and then we just return that back to the user. So most of the work here is happening in 2 different places. The first is like actually calling the embedding store to pull the nearest neighbors. And then the second is this QA with sources chain, which is taking as an input those input documents that we pulled as well as the query. And then it's passing those into a prompt that it sends to GPT-4 and uses to answer the user's question. And so we can pull up LangChain and look at what this, this QA chain is actually doing. But I'll pause here first and see if there's any questions. Yeah. Mm-hmm. Yeah.
There'll be quite a bit of latency there.
Well, try it out. How's the latency look?
Say again?
How's the latency look on Discord?
No, I did not try, but I'm asking because the chunk size, the sources could be of any arbitrary length, right? And also another question I have is, so we are assuming that the question, because you're looking at the nearest neighbor, right? So the question must be related to the source, and you're getting all the sources related to the question. So how accurate is that similarity score going to look like?
Yeah, I mean, I think there's no way to answer that other than just to tell you to try it and let me know what you think. It works surprisingly well, but this is a pretty naive implementation of this. So I think a next step for this would be to look at the queries that users have had in Discord, figure out where it's working well and where it's not working well, and then figure out what part of the system we need to tune in order to make it work better. So is it that we're retrieving 3 documents, and each one of those documents is a chunk of 500? Is it that we normally retrieve the right chunks and our prompt is not right? Or is it that the more likely thing, which is that we don't always have the right information in the context because our information retrieval system is not working that well? So the first thing we'd want to do is diagnose that, and then the improvement that we'd make to the system would be dependent on the diagnosis that we had. Cool. Okay, so let's take a look at LangChain. Let's see if we can find this in GitHub. So LangChain is constantly changing, so I hope I remember where this is actually located. But one of the ways this is organized is you have a bunch of things in chains. And one of these chains is the QA with sources chain. And so if you remember, we had this function called load QA with sources. So let's look in this QA with sources chain. And let's find this function that we were calling, and let's look at what this function is doing. So one of the unfortunate things about LangChain is that it's doing something pretty simple, but it's wrapped in a lot of layers of misdirection. So it's going to be a little bit harder to explain this than I think it should be. But yeah, let's see if there's a better place here where we can. I don't think it's the most efficient to walk you through the whole code. But let's see. Yeah, there's a lot of code here to do something very simple. Yeah, so here's an example of what's going on under the hood. Just to I think the most interesting thing to look at is just the base prompt itself. Because this determines the logic for how the chunks and the question are combined to produce an answer. And so the simplest version of this is this question prompt template. And so this is, okay, so I think in this case, this is a version of this prompt that is meant to be performed over when you have more chunks than can fit in your context. Just as an example of one of several variants that they have here. And so the way that they're doing this is they have this question prompt template, which says, hey, I'm going to give you a piece of a long document. And then what you are supposed to do is determine whether this text is relevant to answering the question. So here's the context, here's the piece of the long document, and here's the question. And then the model responds with any relevant text. So this is something that's meant to be applied to each chunk of the text independently. Then once it's applied to each chunk of the text independently, each of these results are passed to this combined prompt template. And what this combined prompt template is doing is it's combining these extracted pieces of the text and creating a final answer. And you'll notice here that like, if you don't know the answer, just say you don't know. Don't try to make up an answer. Which is like a common instruction that you'll find in like many, many prompts. And they also have like a couple of few-shot examples here, just to like provide the model with additional context, like probably I would guess for the purpose of formatting, to make sure that the model understands the way that it's supposed to format things. And then finally, the question and summaries are passed in here. So this is like, I believe in this chain, they have like different ways that you can run this chain. They have the map reduce prompt, which we just looked at. But then they also have the stuff prompt, where you just basically have a single prompt that says, hey, take the following extracted pieces of this long document and create a final answer by like reading each of these pieces. And so rather than applying this map reduce logic in the chain, where it processes each of the chunks independently, decides whether they're relevant, and then passes those along to a final prompt, instead in this case, what it's doing is just taking all of the results and the question and producing a final answer. And there's a bunch of kind of logic in here that is designed to have like a bunch of reusability between the different chains and prompts that they have. But under the hood, all it's really doing is it's taking these prompts, it's filling in the prompts with the context and the question that you're answering, that you asked. And then it's taking that filled in prompt, passing it to OpenAI, and returning the result to you in a standardized format. So maybe this gives you an idea of like why a lot of people don't like LangChain that much, how difficult it is to explain what's actually happening under the hood here. But it's still a useful tool if you want to like try out a bunch of these ideas quickly. Any other questions on this? Yeah. Yeah, so we return 3 chunks. Each of those chunks is size 500 tokens. And then the prompt that we're wrapping it with is like not very much. It's, I don't know, I would ballpark this at what, maybe another 100 tokens? So we're using probably around 1,600 tokens plus the response. And the response is capped at, I think we said 256. So it's gonna be around, it's gonna be under 2,000 tokens for each one, yeah. Any other questions? Mm-hmm.
Basically execute task in an orchestrated fashion, or is it just like a software app where you just tell, like, do step A, B, and C, and so on?
LangChain is a library that just wraps the vector database and prompt functionality, or vector database and LLM functionality, and then includes a bunch of examples of how to combine those 2 pieces of functionality into a chain with a specific predefined prompt. And so what it's useful for is like, there's probably around 50 or 100 prompts, like 50 or 100 chain examples in here. And so if you don't really know what kind of chain you want to use, you can find a lot of useful stuff in LangChain. Well, a lot of useful ideas of different chains you could run. But the functionality is pretty thin because it's just Python code that wraps those 2 things, like that wraps the vector database and the LLM, combines it with some logic and a prompt, and then calls those other services. And so you would need to take care of hosting this and doing any like infrastructure side of it yourself.
Got it. So in this example, the compute is happening in the modal or the Docker container where you're running this, right?
So in this example, the compute is running in the modal, like the Docker container that modal is managing. And then it's running this LangChain library, which manages the calls out to these other services. So the calls out to MongoDB and Face and OpenAI. Yeah, so these prompts are all like structured as few shot. So they have like, they have some instructions, like, hey, here's what you should do, and then they have some examples. And I think like, I suspect that really like these examples are more useful for like ensuring that the model responds with consistent formatting than anything else. Because this is a pretty general prompt, right? So you wouldn't really expect the model to be able to understand how to do question answering well just from 3 examples. So we're using Gantry for like logging all of the inputs and outputs so that we can use those for improving the system after that. To the whole system, yeah.
Totally different question. I'm unable to access the Discord link. Do I need an invite for that?
Yeah, so there's an invite code that I had in the slides here. Is this the?
I can't access that. It says it's invalid link, or maybe I'm not invited. So.
Was everyone else able to use this? Works okay? Are you maybe already in the Discord? Is that possible? Okay. Well, I can send around and like I can try to make another link and send it around via email as well, so folks, so folks can stay in touch with each other. And there's a bunch of other like channels and stuff that are pretty active where people are talking about LLM apps. Cool. Well, that was sort of like a quick tour of that code base. I would encourage you to like try running it on your own and try to make some improvements. I think there's a lot of it's intentionally a pretty simple implementation of this Discord chatbot, just to show you like kind of how simple these things can start. But there's a lot of room for improvement, like tuning the chunk size, trying out different prompts, trying out different chains, like adding some more advanced information retrieval techniques that could probably make this a lot better. And so I think it's a good starting point for trying out some of these things on your own. But I guess to kind of wrap things up, I think like the main thing that I want folks to take away from this is, it's really cool time to be working in AI because we have access to this incredibly accessible and highly magical feeling technology. But LLMs may feel like magic, but they're not a silver bullet. And in particular, it's never been easier to build prototypes with LLMs, but it's just as hard as it's ever been in ML to build like really consistently working production systems. And there's a few reasons for that. The first is it can be hard to get LLMs to do exactly what you want. It's easy to get them to do something reasonable, but it's hard to get them to do what you have in your mind. And so we talked about different ways of achieving that, like prompt engineering, task decomposition, and fine-tuning as ways of specifying to the LLM what exactly you want it to do. LLMs also, they know a lot about the world. They're trained on the whole internet, more or less, but they don't know everything that you want them to know. They don't know about your problem. They don't know about the things that happened yesterday. They don't know about your emails, your company's documents. And so we talked about like a set of techniques that you can use to give LLMs broader knowledge of the world by augmenting them with tools and information retrieval, and giving them ways to pull in other data to use to answer the question. And then finally, it's really hard to go from a prototype to a reliable production system. There's all kinds of different things that you can try. How you chunk up the documents, what is the text of your prompt, like how your information retrieval system works, all of which there's no right answer to how to do it. It's all empirical. It's all just based on like what is needed for the specific task that you're trying to solve. And so we talked about a more systematic approach for building up from a simple application to something that works well for your use case, that's grounded in these ideas of LLM ops and a process for doing test-driven development where you try to ground the changes that you make to your system in measurement by running evaluations, rolling out your system to a broader set of users, capturing the feedback that you're getting from those users, using that not only to make your prompts better or your whole system better, but also to make your evaluation better so that you can create this sort of like positive flywheel effect over time. And we put it all together into this like kind of what's emerging, I think, is like a standard anatomy of an LLM-powered application, where the user's request is processed by an LLM app that is under the hood just a base model from OpenAI or Anthropic, or maybe one that you're hosting on your own. But that model is wrapped in a lot of logic. That logic includes the instructions that you provide to the model in your prompt or your chain of prompts, as well as the way that the model can access external information. And as a developer of this system, you want to build an improvement system around it that you can use to understand what's working and what's not working, and use it to like make changes to your LLM app to bring it closer to what your users want. And we talked through the different pieces of this system, as well as looking at like 2 simple examples of concretely what a system could look like. One that works pretty well today in the Discord bot, and another that works really terribly today, but might be the easiest way to build these things in the coming months, which is the OpenAI Agents API. And yeah, that's most of what I wanted to cover today. Happy to pause here and answer any additional questions that folks had, or talk about whatever else is on your mind about building LLM apps.
Is it a reasonable practice to say when you get a prompt, a question from a user, Q&A, and then you find a nearest neighbor, find a bunch of chunks. So that's sort of deterministic. So next time around you get the same question. Is it reasonable assumption that I can cache the results and then serve it instead of going to OpenAI each time? And what's your thought? Because I know going to OpenAI each time also gives you different results. But if the user is already satisfied with the current result, you might always pick it up from the cache.
Yeah, I think caching is a very reasonable thing to do, as long as you're aware of the trade-offs, which is like if you update your embeddings or you update your prompts, you need to remember to invalidate the cache. And if you want the results to be non-deterministic, like if you want the user to be able to ask the same question multiple times to get different answers, you probably don't want to do that. But it's pretty, like I see most people doing caching. And yeah, it can save you a significant amount of money.
Well, based on like what you just mentioned, I don't know if you saw that in the OpenAI Dev Day, they actually discussed about this kind of new functionality they are planning to release, the seed, when you can actually specify the seed of the model, so the model is going to be a little more deterministic rather than probabilistic. So how do you think that this could potentially be implemented in a model that is more a probabilistic model?
How the caching can be implemented?
How you are thinking about the seed? You heard that they're planning to kind of, if you specify the seed, the output that you're gonna get should be the same every time that you call the. Is that possible, or how do you think that this can be implemented in these kind of systems?
Are you asking how a seed can be implemented for systems other than OpenAI? It's surprisingly tricky. That's why it took OpenAI so long. I don't know, like. You just need to make sure that you're controlling all the sources of randomness. Usually there's sources of randomness that like pop up at different points in the sampling process, where you're, normally like when you're sampling an output from an LLM, what you might think you might do is you might at each step select the most likely token, but it turns out that selecting the most likely token at each step does not produce the sequence that is most likely. Instead, what you want to try to do, ideally what you'd want to do is you'd want to select the most likely sequence of tokens. But that's computationally infeasible because there's a massive number of possible sequences. Because sequences can be pretty long, and each token in each element of the sequence could be any of your tokens. So it's a huge explosion of possible sequences. And so the way that people typically do this is through sampling and different sampling processes using like techniques like beam search to like do an approximate way of searching over sequences. And that's where a lot of the randomness comes from. So never really tried to make this work in open source LLMs. I'm not sure how much of it is like built in versus things that you need to be careful about. But generally, like I think with sampling from deep learning models, I think the things that people get wrong are like, oftentimes you need to set many random seeds. Like you need to set your NumPy random seed, your PyTorch random seed. And like one way I've seen this go wrong in the past is like you set one of those random seeds, but you forget to set the others. And there's like some additional randomness that you're not controlling for. Yeah, so temperature zero also does not guarantee deterministic outputs. And also I think for evaluation, I would set your temperature to whatever your temperature is going to be in production. Because the characteristics of the outputs will be different with different temperatures. And so I think the seed is the right way to do it. Because you want to have like an output that looks like production, but it just doesn't change. And if you change your temperature, then will make it more deterministic, but it will not make it, but it will also make it different than what you're going to see in the real world. I think I would check with them on that. It's generally available as of maybe a month ago. So I think it's relatively production grade. I haven't seen people use it for like large scale systems. I think where I see people use it more is like for like data science kind of tasks where you're not necessarily like running your whole application backend on it, but you're running some of your ETL logic or like something that you need to parallelize, but you're okay with it failing sometimes. So more like data science workflows instead of like what most people consider production workflows. But I don't know that that means you can't use it for those workflows. I just haven't seen that as much. Yeah, I mean, it just totally depends on what your company does. So normally I see modal being used either by like startups or like data science teams or ML teams within companies for stuff that they want to have more within their control. And then for bigger companies, if you're building like a web application, your company's probably making a decision about how to build that independently of how you're building your LLM systems. And so mostly companies will like piggyback on the existing infrastructure that you have for that.
With temperature zero, where is the randomness coming in from?
Yeah, it's a good question. I was hoping no one's going to answer that because I don't actually remember. But try it. It's not deterministic. Yeah.
Okay. One more question. How much for AskFSDL? How much do you guys pay for it to be hosted right now with OpenAI being used?
Like very little. I want to say it's less than $10 a month.
Oh, okay. Thanks.
And it's like people use it. It's not. Yeah.
Is temperature zero about randomness or is it about annealing?
Temperature zero controls the sampling process. So the effect is that higher temperature means that the model does not concentrate as much on the most likely tokens. It samples more broadly from the set of available tokens, which makes the outputs more random. But setting temperature to zero does not make the outputs totally deterministic.
In the LangChain, can you chain like multiple LLM like models to run a response? And if that's the case, do application developers have to worry about what kind of embeddings you're using? Because if one LLM uses a type of embedding, like in OpenAI in this example, and if the other one uses else, like do you have to like ensure you have the different embedding models stored in your vector database?
Yeah, so LangChain does let you swap things out pretty easily. That's one of the advantages of it. It's like, if you want to try out both OpenAI embeddings and Cohere embeddings or something, like they have the wrapper code that they make around them, makes them not totally interchangeable, but more interchangeable than they were if you're just calling those companies' APIs directly. And that's one of the advantages of it, I would say. But in terms of compatibility, like yes, you can't really compare directly embeddings from one provider to another, or even from one model to another. So you would need to re-embed your entire corpus in order to run that experiment. Well, maybe we'll take one more.
Aurora and all these databases, they are coming out with all these vector indexes, right? So is there like a real use case for Pinecone and all the newer ones? Because I see Aurora is like one solution that you can use in production systems where you can put your data sources / you can also do vector.
Yeah, I think like, so the decision tree I would have is like, do you actually need an embedding database at all? In some cases, no. Like, you can just do, you can just store your embeddings on disk, and then compute the embedding distances manually by hand, which is not that dissimilar from what we're doing in this example. Instead, we're using an embedding index called face, but we're just storing that on disk, and we're running all of the similarities locally. So the question is like, when would you ever need more than that? And the answer is like, well, one reason why you might need more than that is if you want your search to be more complicated than just vector similarity. So if you want to have other information retrieval functionality. Another reason why you might want to do more than that is for performance or scale reasons. Performance, scale, or reliability reasons. So if, storing a vector database on disk on your machine is not going to be very good for reliability, scale, parallelization, things like that. And so you might want an actual database for that. Yeah, so like if your index doesn't fit easily on a single machine. Yeah.
My question was mostly not on the on memory itself. My question was mostly this newer generation database companies like Pinecone, VV8,
right,
and all these companies. What is their business case while others can easily adapt, like Aurora and MongoDB, and all these people can adapt and provide vector searches natively.
I would say,
and that way you can also minimize. Let's say in the demo you had a MongoDB and a Pinecone. So if you actually go run it in production, you have to monitor both. Right? Operationally, it's expensive. Right? So while if you have just one database, you can just do everything with it.
Yeah, I think you can just have one database for a lot of cases. Like you could just, you can run vector similarity search in Mongo, in Postgres, and like most kind of commonly used form databases. And so for a lot of companies, I think that's the right decision. But I guess the business case would be every technology shift has led to a new form of database. Mongo itself, you can make the case for like why should Mongo exist when you can just use Postgres for everything you'd use Mongo for. Well, turns out that people use databases for a lot of stuff, and a lot of like really core development tasks depend on databases. And so databases themselves are highly specialized to the tasks that people use them for. So the argument that I think you would make about using something like Pinecone is, well, we are going to be doing a lot of vector DB operations, and so we should use the tool that's best suited for the job. And that could end up being cheaper depending on your use case than the operational cost that you pay by now having more than one database that you need to maintain.
For the test-driven development section, are there any existing resources or frameworks that are available on the internet, or is it still very new and very like?
Still very new, yeah. I think there's like beginning to be some resources on evaluation. So OpenAI has an open source evaluation library. There's a number of startups that are working on LLM evaluation, including us. We're building some stuff around this. But in terms of like the entire test-driven development framework, I haven't really seen anything yet, but I think it's coming. And it's something that you can do on your own. Like you can, it's not that like no one is doing it. A lot of companies, especially the best companies, follow a process like this. But there just isn't really something that has been, packaged up and systematized. And one of the reasons for that is because the details of doing it depend a lot on the thing that you're trying to build. Cool. Well, let's wrap here. Yeah, really appreciate you all attending the class. Hopefully you learned something from this. Always really interesting to hear questions people have and stuff that you all are working on as well. So would love to stay in touch. I guess you all are in the Discord, or feel free to message me on platform of your choice if you weren't able to make it in the Discord, and I can get you an invite. And yeah, thanks for being a good audience.